perspective on cosmology. And this is based on two papers, recent papers, one with Obeid, Uguri, and Spulineko, and the other one with Agrawal, Obeid, and Steinhardt. So, so perhaps I should say what's my main aim in this talk. My main aim in this talk is, which is part of this ideas related to Swampland, is to discuss aspects of cosmology in this setup. And the main aim is that in cosmology, perhaps we have not been very, we have not brought stringy ingredients too much to bear on it. And I will try to motivate that not bringing stringy aspects has made cosmology difficult to fit within string theory, the usual paradigms of cosmology. And so these aspects, by no means is to turn off some directions that people have done in string theory. It's great that people have studied all these different aspects, and they should continue studying the conventional ways of fitting cosmology in string theory. But there are new directions that might be interesting, and I'll try to motivate you, regardless of the conjectures that I'm going to discuss. There are new directions in string theory that we should be exploring, and that's what my main point is going to be. Not to say something is wrong, or this is wrong, or that's wrong, but more precisely, there are new directions, and so I want to expand the possible sets of how we can connect string theory to experiments, which potentially can have more predictive power, actually, than the current way we are trying to do string theory connections with cosmology. So that's my main aim for the talk today. So, so what I will first do, I will first review for you some basic aspects of cosmology. So I will call cosmological facts. And also I will talk about particle physics facts. So let's start with cosmology. Early universe, very early universe. So let's talk about the past of cosmology. We start with, conventionally we thought there was the Friedman-Robertson-Walker kind of setup, but this gets into problems, and in particular the homogeneity is one of the issues, for example. Causal connection between different patches of the CMB gives you some issues with this FRW picture, and that is one of the motivations in particular, as you know, of inflation, where we have a period of cosmic acceleration at the beginning, enough to make the observable parts of the FRW of CMB that we are getting today in causal contact and causing homogeneity and this and that. So there are very nice features, and inflation does that with relative ease. So inflation, which is basically a very simple idea, at the outset of it, from the effective field theory viewpoint, looks a very simple idea. It seems like it solves a nice problem, and why not? So that's the attitude that inflation people have, and I can see why. It's a very nice, simple idea, and it gives macroscopic features, and the basic features of homogeneity features comes out right, including also fluctuations which are imprinted in the context of inflation by quantum fluctuations, which when they get frozen into the fabric of the space-time, then it gives rise to the galaxies, etc., and they fit with all these various pieces that we have seen in the data, and so there's a lot of evidence for this simple idea. I should say that the amount of check that has gone to it is not as much as you might think. That is, basically homogeneity has been checked together with slight fluctuations. Those are the basic aspects that have been checked. So even though you see this power spectrum of this angular thing and it looks like a peaks, all this matching and all that, the amount of data that goes to it as far as inflation is not as much as you might think. So it's not like every little peak is a new story of inflation. So it's not like that. But still, I will still give credit to the fact that the idea is very simple and it seems like to fit in a nice framework.
Can I ask a general question?
Yes.
Are we going to be able to use string theory to decide which approach to cosmology is the correct?
Well, I mean, decide is a strong statement here, but I will just guide you through what people are doing and what my view is, and these are the people, we can decide what we want to do. So one aspect of inflation that even at the beginning looked a little bit strange was the fact that in order to get the potential things that to work, you needed to have a relatively flat potential like this, in terms of the inflaton field, where the field rolls, and it stabilizes here, and it radiates, and it stabilizes here nicely to something of the order of 10 to, now we know, of the order of 10 to the minus 122 in fundamental units. And maybe this starts something of order of m got to the fourth or 1 or something. So it starts with some huge thing and then suddenly rolls down. So, well, that already is a funny feature that people, you know, cosmological constant problem, nobody has solved it really satisfactorily. People blame it on anthropics and this and that, but that's one issue. The other one is the relatively long range that you have to move in the field space in order to get there, and people say, well, okay, why not? We can have such potential. And Stravinsky, for example, originally when he was talking about these kind of models, wrote potentials which are very similar to what people still consider today as potentially interesting for cosmology. So there are examples like this, and people have already discussed these. Now, already this raises flags in the context of discussions we have had in the workshop. Namely, delta phi in Planck units turns out to be necessarily bigger than 1 to get a long enough period of inflation to give you the 60 E-folding that's necessary in the inflation in order to explain the homogeneity that we see in CMB. So that's already a little bizarre. Now, does it prove it's not possible? Well, not necessarily. Gary talked about possible models. For example, maybe the axion monodromy models or this and that, which potentially can make this maybe 5 or 10 in fundamental units. So could. Whether it does, it's questionable yet. It's not clear whether there is such construction. There are, I think, people, naturally you're pushing the string theory to its extremes, and so their calculational power is limited, and so we have issues whether or not we really have established existence of these things. But I would not say we have ruled out such a possibility. So there's possible that, you know, you could say that just to give a positive spin on this one, you say, look, phenomenology that we live in is very fine-tuned, so maybe this is also fine-tuned, and maybe it's possible to get these. Yes?
There are also models where delta phi is small, right? There's
Yeah. Well, this is the typical models for the inflation, and then there are other models which have other problems. So we can talk about all possible issues of models, but the models that people now favor, again, it's not universal. Most people believe in inflation, believe in these what's called the plateau models. That seems to be the most popular one. By no means the only models. People can add various things to it. So anyhow, so this is certainly possible. You could say phenomenology is fine-tuned. Hierarchy is an example. So maybe this is also fine-tuned, just like cosmological constant. So who's to say? Okay, we cannot say just because it looks fine-tuned it's bad. We have learned that lesson. In fact, the lesson from Swampland is that some things are naturally sometimes fine-tuned, and that's sometimes there are good gravity reasons that we learn later. So effective field theory is not a good guide to decide what is fine-tuned. That's what we are learning in the context of the Swampland. Some of the intuition about the fact the field theory is what is fine-tuned or not may not be correct in the context of a quantum theory of gravity. That's possible. So maybe there are models like this which are not, which could happen in some form, but again, in the context of string theory, which has quantum gravity, it's hard to get them, at least, if not impossible. So this is a potential issue that has to be dealt with. Okay. So that's a brief description of where so this is the current paradigm of current universe. That's how we believe could potentially explain what we have in the universe observed today, and that would be the very early universe. And this could be the stringy realization potentially in the context of the axion models for other kind of string models. But it's interesting that nobody claims to have gotten delta phi, let's say 20 or 30 or 40. So we are at the borderline of possible possibilities within string theory, even the constructions that people are claiming. So it's not like parametrically we can make this large in string theory. It is difficult, and we know that's not easy or impossible. Whether or not you can make it 1, 5, or 10, at best, it's fine-tuned, at best. So that's the point. So we could say potentially we can put this in string theory in something which, even in the quantum gravity context, namely in the garden variety string context, looks fine-tuned. But still, it doesn't rule it out. It's possible, but it looks fine-tuned. Okay. So that's the past cosmology. The recent cosmology. Well, since it was discovered in the late 90s that we have dark energy, despite the string theorist effort to prove it, and we failed, so that was good that we failed, and people found there was a dark energy. And people try to find models, and naturally string theorists had to find models which fit the observed data, the dark energy. And the most natural thing was to find a model like this. Like you have a scalar field would have energy 10 to the minus 122 or so in fundamental units, in Planck units. So how do you get these? Well, you have to scan of the order of 10, at least this many, inverse of that many vacua, roughly speaking, if you have a random like distribution between 0 and 1. So you could say that since we have so many choices, why not? We can get such thing. Just an anthropic principle could explain why we are in one of these. So that was the context that motivated string theorists, for example, KKLT and supercritical strings, supercritical dimensions, and so on, and other efforts to try to explain or come up with models of current universe, the present. But people attempting to actually realize this in string theory are, so there are some claims that there are attempts that have realized this, some people claim, and there are some issues that raise, as we heard yesterday, the issue of, in particular, the anti-D3 brane introduction and the back reaction, and the issues surrounding that are subject to debate still, and so people have different views on it. Now, one thing that in the original KKLT paper was mentioned, and this is actually something which is, I want to say that that's an issue that was not necessarily clear, is that the issue was that can you find something which solves their problem? And in some point they needed to solve a hard problem, and they say, well, there's so many choices that one of them will do the job. So in other words, once you face a hard issue, like this small number or something like that, you could say, okay, since you have a huge number, why not? Okay. Now, the why not from the effective field theory sounds reasonable, right? If you take a random function, why not? Indeed, why not? You can have, if you have this many vacua, why not one of them like that? That's fine. But why not might have a non-effective field theory description, which is the Swampland kind of problems, which may say why not, but we don't know exactly how to describe it in effective field theory language. So this why not issue, so this idea that people use again and again, which I believe is a little bit dangerous, and in fact, it is dangerous in the context of quantum gravity, is to say effective field theory is fine, and genericity argument. Genericity argument with an effective field theory mindset is incorrect. What we think as a generics thing in an effective field theory sense is not necessarily what a string theory involving a consistent quantum gravity may prefer. So our intuition is not guided correctly when we just look at effective field theory. So that argument is not necessarily reliable to say we have so many choices, therefore one of them would work. That's not a good enough argument. So many people working on this subject basically point to the fact that the number of possible constructions is bigger than this, therefore there must be one like this or something like that. So this kind of, a lot of them goes like this counting argument rather than actually constructing it. And but there are some people who have claimed they have constructions, and then the issue in those cases would be, and I mean, I sympathize because the computational control is very difficult in these kind of contexts. You want to have string coupling small, the curvature is large, and this and that, and we will see that there are various no-go theorems unless you have to violate something which is not easy to realize in these contexts, and that is the main problem with this. So again, KKLT may or may not work. At least may work, but also may not work. We don't know. May or may not. It's still under debate. So again, I don't want to say if it's. I don't want to say anything strongly against or for it because it could not. I don't know. So we'll leave it like that for now. So as you can see, this as Dave's question, whether or not we will know, there are attempts, but all of the attempts, precisely when we are trying to match our universe, looks a little questionable, whether we have managed to do it or whether it's highly fine-tuned, one or the other. Everybody agrees that this number is highly fine-tuned in string theory. That is no doubt. So we have to deal with that somehow. And so either if you take a KKLT viewpoint, then you will have to deal with that too. Future. Well, what is the future status? Well, to gain insight about the future, there's a puzzle, which is, I will reformulate it, not the usual way it's formulated, but in some sense equivalent to it, is that if you take the age of the universe today, is of the order of the scale set by the cosmological constant in the fundamental units I'm doing again. So
It was first observed, I guess, by Dirac.
no, I guess Dirac said in the context of maybe matter density and so on, perhaps. Here I'm using the dark energy itself. So, but yes, in some form, that's why I'm saying it's in different form. So yeah, in some form it's like related to matter density and so forth. But in this context, I'm talking about just the dark energy. That's right. This is what's called a coincidence problem. Why do we live in such an age which is set exactly by the natural time scale that you get from the dark energy? Why is that? It's a little bizarre. So just so you know, this is the usual thing. You know, you get a dot over a squared is of order lambda. So the natural time scale is 1 over square root of it. So this is the natural relation between the dark energy and the time scale set by it. I'm setting m Planck and all that to 1. So this is a funny feature. So roughly speaking, the age of the universe today is roughly 10 to the 61 or so in Planck units. Okay, why is this? This is called coincidence. We happen to live in such a time. This will sound very strange in this context, because if you have a context like this, if you ask what is a typical lifetime of a universe sitting in a de Sitter space, it could be arbitrarily long, because there's no telling what is the height of this potential. And people even have debated whether you can make tunneling in the de Sitter, like Tom Banks and so on, debate whether that's even possible. But at any rate, regardless of that issue, there's no reason it has to be, if there's a metastable, there's no obvious reason why it has to be short-lived. Typically, it would, I would say, a random one would be very long-lived, depending on this height. And so there's no relation between this height, the dark energy, and this height or the time we have to live. In other words, then this would be truly a coincidence problem. We happen to live exactly at this time, but we could have lived trillions and trillions, 10 to the power of trillion years later, and still would have been okay in some sense. Okay, that would have been a possibility. So this would be strange. This would have no answer in the context of this kind of picture. So if you take the de Sitter viewpoint, this continues to remain a puzzle. Okay, so this is facts I wanted to basically review for the cosmology.
Sorry. But doesn't this simply tell us that that lambda started dominating not so long ago?
This is related to that fact. This is related to the fact. So in that sense, you could say the fact that now the lambda is dominating is related to the fact. So we have just come into when lambda begins to dominate. Right. Why not much later? Why didn't we come in much later when it was always expanding? What was the problem with that?
If I assume a matter-dominated universe, then I get that the age of the universe is some number of order 1 times...
Well, as Martin said, that was another version of stating the coincidence. Since it's only in the recent epoch we have gone to an accelerating phase, they will give you the same kind of numbers. That wouldn't change the kind of statement. Okay, good.
You somehow put in here some kind of, or well, I mean, to some extent it relies on how sentient beings are
I do.
I mean, it's somewhat weird. I mean, to some degree, we know that it takes a while for stars and galaxies to form.
Yes, and you have formed. Why did we come now?
Well,
we could have.
Time more or less when they formed the first one.
Why did we just happen just at the very birth? We could have come 10 to the 10 to the 10 later. What's the problem?
I don't think so, right? Wouldn't then, I mean, how long are stars formed? In the universe with a cosmological constant, I'm not sure that is possible. I mean, it can be maybe 10 times later.
You could blame this on the properties that the stars may have disappeared or something like that. You could play that game, but it's not. It still will be much longer. We have much longer to go to get
10 or 100. I don't think it's
100 or.
10.
You could try to explain it by other means, like other aspects of the matter structure.
Yeah.
But from the viewpoint of the dark energy, it's still puzzle. So there's a coincidence there which is still puzzling.
You may just make a comment. There's some papers by Raphael and collaborators, in the context of the measure problem. Like if you have a choice, say use the causal patch measure, they they discussed how they think that should be natural in that context.
Okay, they try to explain this. Okay, I'm not aware of that, but okay, that would be interesting to study. In the context of the de Sitter, certainly, I mean, I do not know how you can, I mean, in the context of string theory, I do not know how you can say this height is related to this height.
Yeah, I mean, you add a mesh, you have to make an assumption of a mesh.
Yeah, the measure of the string vacuum to me is very suspicious, to be honest. I mean, yeah, it's difficult to believe it. What do you mean by the measure of the string vacuum?
Well, that's another conversation, I guess.
Well, it's the same conversation because you're saying they make a measure. So I'm just saying that we cannot rely on such statement. So it is certainly, there is a coincidence problem, and depends on how you want to view it, there's an issue there. So I just leave it like that. Okay, I will go to the particle physics facts. So we know that we have a standard model, the visible matter sector, maybe embedded inside, presumably inside some kind of grand unification scheme, and dark matter. These are experimentally known. We know we have dark matter. We know we have standard matter, standard model matter, and we know that the energy, roughly speaking, 5% of the energy universe is in the standard matter, and maybe 25% or so in the dark matter, and so on. What is the picture? How do we think about this picture in string theory context? Well, there's a natural setup in which you can imagine how this arises in string theory. Notice that the standard matter content is asymptotically free. Right? We could have had a huge number of generations. We only have 3, and so on. And so the fact that you're getting something which is actually explainable by field theory alone is striking for grand unified theory. In other words, even if you take M Planck to infinity, you would get the gut. In other words, the gut does not rely on gravitational effect to make sense. You don't need, if it was not asymptotically free, you would need some gravitational aspects to complete it. So this theory is a standalone object, which means this guy could potentially have made sense even if you sent M Planck to infinity, even if you send it to infinity. Which suggests that if M Planck going to infinity in string context means the volume gets bigger and bigger of the internal manifold, means that this is coming from a local region of the compactification geometry. So it's a very natural model to believe that the standard model comes from you have some manifold, and somewhere there's some local region which survives even after you take the manifold to be bigger and bigger. Yes?
We don't really know that for the Higgs sector. Scalar couplings and Yukawa couplings.
The Higgs sector is you mean in terms of whether it's asymptotically free or not? Yes, that's true. So I'm talking about the matter sector more precisely. So the Higgs sector, right? So the Higgs sector, for example, could be somewhat connected to our universe, but could be somehow a little bit needing the gravity effect. In fact, I will come to that in some context. So that might be that's relevant to my talk discussion at the end of my talk. But for now, let me just say that the standard model, like the number of generations and the gauge group and all that, nicely fits within the context of local region in the space of the compactification. Now, in any compactification we are aware, or in garden variety compactification we are aware of in the context of string theory, another way of saying is that you can imagine having a D-brane like wrapped around some particular region here, and so forth. And these regions are positively curved geometries that can contract, so differently can survive even after you make the rest of the manifold big. That means M Planck going to infinity does not destroy their existence, and that's fine. But there are other fields. In string theory, it's very difficult just to get this one thing, and you get many other stuff. So, and I think it's morally that there should be a theorem to the effect, even though I do not know how to precisely formulate it, the matter sector of any quantum gravity is morally not asymptotically free. Morally not. In other words, if you include everything, you have to get extra junk. It's not just pure field theory. It has to have something else. In other words, gravity should be good for something. Gravity is curing something. What? Well, the matter stuff is not working, so gravity is okay. It's my task to fix things. So gravity is needed for them to fix. And I don't know how to precisely formulate this conjecture, but I would not be surprised if there's a Swampland criteria, which all the effective field theories that we get in the concept of quantum gravity are not asymptotically free. And this would morally imply that in addition to our sector, which is asymptotically free, there must be other stuff. this other stuff that should come somehow from other modes in the Calabi-Yau or other compactification would be the reason that we have dark matter, in a sense. So it's a nice kind of picture that why do we have dark matter, and how we could get a standard model could fit. And maybe the fact that it's 5 times bigger is not that unreasonable, given that you take a region in space and the rest of them, maybe there are more structures allowed and so. So it's not at all exotic that we are a minority. We are a minority because we're a tiny piece of the space somehow. We are not probing the whole aspects of the compactification geometry. So it fits. It gives a relatively nice picture, I would say. And the F-theory model building concentrates on these kind of possibilities where the local feature of the geometry gives you the matter structure that we are made of. Okay. But dark matter is at best very weakly coupled to our sector. It hasn't been detected other than this gravitational effect so far. So at best, it's very weakly coupled to our sector. We do not know what is the exact coupling because we haven't discovered it. Gravity certainly mediates between them and us, but we don't know what it is. But it should be weak. That for sure we know. At best, it's very weak. So the dark matter sector should somehow be either localized in pieces that are far from us, or somehow scattered enough so that it doesn't interact with the wave functions that we are made of localized in this space. So it's kind of orthogonal, or at least very little overlap. So that must be, otherwise we have a problem. So the dark matter is so weakly coupled. So there's very weak interaction between them. If more than gravity still, it should be very weak. Okay. Now there are other aspects of this piece that looks nice. Namely, if you think about the local geometry, we have learned in string theory that's easy, or at least it's not that difficult, to freeze moduli locally. That is, you can easily consider local pieces where a sphere of a size gets frozen. Sphere gets frozen by fluxes locally very easily. We have very workable models. For example, we understand confinement of n equals to 1 supersymmetric QCD that way, based on string models which are local. And so we understand how locally you can freeze a geometry like a sphere or some matter. And typically the coupling constants of the theory get related to the volume of the internal geometry. So for example, the fine structure constant will be related to the volume of maybe of some geometry like that, the standard model of the piece that the standard model comes from. And it's frozen, so that could be no problem, and you can have a geometry like that. And then therefore, it's not surprising to say that these do not vary in time because they're frozen. In fact, there are bounds like the fine structure constant varies very little. So if you go from z equals to 1 to present, from the redshift value from z equals to 1 to z equal to 0, we know there are strong bounds of the form delta alpha over alpha is less than 10 to the minus 6. So it kind of is a frozen piece of the rest of the geometry. For sure it's not. Now, we cannot be completely sure if the rest of the geometry is frozen or not. We cannot be sure, but we are sure about the dark matter sector. The standard model sector looks very frozen. If it's moving very little. And that's not exotic. We can arrange easily like this. But we do not have as clear a picture about how the rest could or could not vary. Of course, if the rest of the geometry is changing in time in some way, it will affect the dark matter sector from what I said more strongly than our sector potentially. So that would be interesting also a question for the dark matter sector. Okay, I think that's all I wanted to say about particle physics and how it could potentially fit in string theory. Any questions? Okay, so then so let's go back again to cosmology, to the inflation question in the context of cosmology. So we said the stringy construction of inflation runs into difficulty. And at best difficulty does not mean insurmountable difficulty, but it's difficult. And at best one has to use very uncontrolled regimes of calculations perhaps, or very fine-tuned regions to get it, potentially using using the string ideas. And de Sitter, again, as I said, is the kind of why not? If you have a huge number of vacuum, why don't you get it? However, now I will try to explain why there are difficulties in a simpler language. Consider M theory in 11 dimension and compactify it to 4 dimension using a 7-dimensional manifold. Now, this 7-dimensional manifold does not have to be Calabi-Yau or hyperbolic or positively curved or anything. Take an arbitrary 7 manifold and take an arbitrary flux turned on it, G flux. Arbitrary. Well, now I will qualify what I mean by arbitrary. Except make it non-singular. In other words, make the curvature and the G much, much less than 1 in Planck unit. In other words, you don't want to have something which is Planckian. So take a smooth geometry with some nice curvature and some flux which is not huge in Planck units. You can consider this class. Well, you would imagine you can get, if you take arbitrary 7 manifolds, look, 7 manifolds, I'm not sure the classification of 7 manifolds, but huge number, right? Do anything you want. Of course you're going to find some situation like this, right? You take a potential and someplace, if you take, what is the potential of? The potential will be functions of all these moduli of all the possible metrics and the fluxes and all that stuff, okay? A reasonable physicist who believes in effective field theory and genericity would have said, come on, there's no reason you cannot find something like this, right? Okay, that's the first generic statement. If you don't know any better, you would certainly say, there's no reason why there wouldn't be a potential as a function of these moduli. At some point, there will be a critical point with positive value, maybe 10 to the minus 120, maybe some other value, some value. Now, Maldacena and Nunes show a no-go theorem that is impossible. This is impossible. That is, if you have a weak regime, if you have a large enough manifold, so you don't have to appeal to Planckian effects, if you take the leading terms in the supergravity Lagrangian and try to find, there would never be an effective critical point with positive value like this. That's impossible. It already shows, and the argument they do is extremely simple and nice. Nothing amazingly difficult. They show it's impossible. This already shows that what we might think about the effective field theory is not necessarily right. Now, this does not rule out, of course, these possibilities because they're assuming Planckian effects are not important. You can have singularities in string theory, of course. Sometimes you get gauge theories from them. Sometimes you do this and that. So we are used to that. So the argument there is that, okay, fine, this kind of de Sitter you will not get from the nice smooth M-theory compactification. Look for other stuff. Okay, so that's the answer to there. But it also proves the thing that bothers physicists like me, that there is no harmonic oscillator for de Sitter space. That is, even if there is, you have to do something exotic, like quantum effect or something which is exotic, Planckian in M-theory, to construct one. But ADS, no problem. Just sending the lambda from negative to positive has such a dramatic implication. There's absolutely no problem, as you know, in M-theory to get ADS space. Very easy. Not just because of supersymmetry. Supersymmetry, of course, helps, but you cannot, their argument specifically states if V is positive, there's no critical point. If V is negative, you could have a huge number of manifolds and fluxes for which there's a critical point. It may not be even supersymmetric. Supersymmetry are easy examples of that, but there's no reason that that's not possible for non-supersymmetric ones as well. So there seems to be something fishy. That is, you either say, okay, we just look somewhere else, this is not a good class, or you begin to ask if there is something swamplandish going on here. Is it possible that this is a beginning hint that there's a problem with de Sitter in the full quantum gravity?
You can use orientifold to evade this theorem.
This is orientifold from the M-theory would exactly look like these singularities. So orientifold does not, in the M-theory doesn't exist in that context. Of course, you can talk about, well, there's a Hojava-Witten kind of situation which would be singular geometry. So you can have similar things to the orientifolds in the M-theory as well. So this no-go theorem applies only to the M-theory, the non-singular one. So they don't claim that they have ruled out de Sitter in M-theory, for sure, or string theory. Their view was that, well, it just means that this is not where you should look for. But it's surprising. It is surprising that for an arbitrary 7 manifold, no matter how hard you try and which dictionary of 7 manifolds you look up, is not going to help you. It's just strange. Now, you could say, well, can I come close to making it vanish like this? Not exactly 0, but very close to 0. Could you make it smaller and smaller and smaller? It turns out there's an easy argument that not only you cannot make it critical, you cannot even come close to making it critical in the following sense. You can show that the slope of the potential as a function of the field is always bigger than some constant times v, where z is some positive constant. So there is a bound. Not only, if v is positive, you can show gradient of v not only cannot get to 0, it cannot even come close to 0. It's bounded away from 0 by some amount. So the slope of the potential is bounded from 0, and you can strengthen the Maldaceno-Nunez no-go theorem to get such a bound. And the argument is actually amazingly trivial. The argument is you just rescale the internal manifold. As a function of that direction, the gradient is never 0 and it's proportional to this. That's it. The argument is that trivial. So using just the boring rescaling argument, you can show you can never get rid of that mode in terms of stabilizing it.
You don't get any bound on C from that, do you?
Well, for the M theory case, we do. For the smooth M theory. So for more precisely, I'm going to write it in a second. So if you go more generally from 11 dimension to D dimension, not just 4, you find that C, the C that could appear in that formula is 6 over square root of D minus 2 times 11 minus D. So for example, for D equals to 4, you get C is 1.6. M Planck is 1 for me. M theory, M Planck is 1. Yeah, I'm doing M theory and Planck is 1, and no. So when you compactify it, you of course go to the Einstein frame of the lower dimensional theory. Yes. Now, is this realized? Could you do any better than this? Well, it turns out that, for example, in 4 dimension, you cannot do better than this. In other words, you can saturate this bound. It's the best you can do for this no-go theorem for the smooth supergravity, because if you take AD as 4 times S7, this geometry, as a function of the radius, you will have a geometry like this. So this is the usual, as a function of the radius, you have the usual minimum, which is the usual supersymmetric one, but you can displace yourself away from the supersymmetric one, and you can compute the slope, and the slope, as you go closer and closer to the origin, approaches the grad v of order of v. So in other words, this bound is as good as you can get, and it's real. The limiting cases can be realized in supersymmetric context by shifting away from the vacuum. Any questions? Okay, so we learned that if there is de Sitter, it is a quantum Planckian non-harmonic oscillator type of situation. We cannot rule it out, but it's that. We have to at least agree that there's something exotic with de Sitter, because these kind of simple ideas show it cannot happen.
But from this perspective, also the standard model is the same.
So I said from the beginning that our universe is fine-tuned. Now, for the context of, for example, hierarchy, there are ideas, for example, Ibanez, I'm sure, will tell us about how ideas related to Swampland can be related to.
Just the Carl Fermans. I mean, Carl Fermans also, from this perspective, Planckian exotic object.
Yeah, so the fact that we live in a very fine-tuned situation in our universe, there's no doubt. It looks, I mean.
Forget about the Higgs.
Well, having Carl Fermi is not that exotic. It's an index term. So that's not, I don't know what you exactly mean by Carl Fermi being exotic.
You can't get Carl Fermi.
Well, you mean from M theory perspective. Yes, okay. That's fair. So M theory, you don't get even gauge group that way. So you say we for sure have SU, forget about Carl Fermi. You have SU2, AU1. So SU2 at least, you don't get that way. You need singularities in M theory. Yes, that's why this is not a proof, and we know in string theory there are other ways that we get it, so that's well taken. So I didn't claim this is a proof. But you would have imagined that there may be one. If de Sitter is not why shouldn't have been one example like this, which is not exactly like our universe? That's the main thing I'm trying to say. This is like kind of the intuition that we have in physics. If something is difficult to get, there may be a good reason. That's the That's the main point I'm trying to give with this explanation. It doesn't prove it. You're right.
Can you say more about the parametric dependence of C in limits where it starts to approach singularities? Or sorry, when R and G start to become not so small?
Well, we don't know how to do that, because part of it is that the higher order corrections, people have not taken into account these arguments. So I cannot argue anything about when the higher order comes in. This is based on just simple Einstein theory plus G squared. You might have R to the 4th, R to the 8th, and if those are becoming big, order 1, they might compete, and the signs might be important, all that stuff. So.
Well, no, just at the leading order, like a small perturbation.
I don't think anybody has studied it, as far as I know. So here, basically, people have talked about the large radius limit and so forth.
I think the bound is just simply not there if you go beyond the...
Well, no, I mean, I still want to be in the limit where things are kind of like smooth, but I want to take into account, like he's saying, like R to the 4th corrections, things like the first order.
Okay, so
just like the first order corrections is like what direction are things going?
Yeah, the question is how much of, I mean, the first order correction is good if that term is small. So, and if that's small, you can ignore it. So the question is, how much are you willing to trade off that term with, and what does it mean to take the first order correction and not all of them? So that's the kind of difficult question. Then there are other examples. So suppose you start with a theory in d dimension. So let me just erase this. Suppose you start with a theory in d dimension and go down to d dimension by some compactification. D could be 10, like in type 2 strings, or some other one, and M theory 11, and so on. If your background, if your compactification that you use respects the strong energy condition, which is not a property of string theory for sure. The strong energy condition is violated in string theory. But if you look at backgrounds which respect the strong energy condition, you find the grad V is bigger than or equal to an expression like this. And if you look at backgrounds which respect the null energy condition, again, this is not a property of string theory. You find, not a general property of string theory, but you can restrict your attention to backgrounds which respect this. Then you find that the grad V over E is bigger than, there's a factor of 2 here, maybe I got this wrong. Something, anyhow, some formula which the detail doesn't really matter. But there's a bound of order 1 in this form. Okay, so these are interesting situations. So you get these kind of bounds. So already you know, for example, if you believe in the sitter or whatever, that our universe cannot be satisfying the geometry has to explicitly violate the null energy condition, because otherwise you get some contradiction with this. Very good question. Nobody has done that. It would be interesting to see if one can use that to get a bound. So the bound that we got was based on the null energy condition. Our null energy condition has a better chance of being true in the context of string theory. But in quantum field theory, we know it's true. In a gravity context, I'm not sure if it's absolutely true or not, but it's a better chance of being true than the null energy. So yeah, so it should be studied. So let me just raise it as a question mark. Then there are examples. There are examples which are not based on, starting from the dimensional reduction to try to break supersymmetry. There's already a string theory which does not have supersymmetry. For the majority of you who are rather young here, perhaps you don't even know about this example. There's a 10-dimensional string theory, which is called the SO16 cross SO16 string. It's in the context of heterotic string, and it's the non-supersymmetric and non-tachyonic and chiral and all that. So it's a nice 10-dimensional non-supersymmetric theory, and you can try to compute what is the cosmological constant of this theory in 10 dimensions. It doesn't have supersymmetry. You don't have to compactify anything. There's nothing. But there's one parameter, which is the dilaton. So you can take the weak coupling limit and try to compute it using the weak coupling techniques in heterotic string. And you find that when you go to the Einstein frame again, you find that as a function of dilaton field, it goes like exponential e to the minus 5 over root 2 phi, where Bigger phi means weaker coupling. So as coupling gets weaker and weaker, you get some exponential potential like this, which again has the nice property that grad V, in this case, is bigger than, well, in this case is equal, but let me just say in this case is equal to 5 over root 2, at least for large phi. Okay, these are examples. Now, interestingly enough, Hertzberg et al. And also Rassi and Zuckerman. I'm not sure if Tim, you're not going to talk about this, are you?
A little bit.
Okay, so Tim will talk about his work as well. But what they showed is that, so they started studying basically the rescaling argument of a combination of the dilaton as well as the volume. So there are two parameters they studied. They studied in the context of scalar curvature being 0, kind of like Calabi-Yau kind of situation. These guys did it a bit more generally. And you can use the arguments that these guys use and extend it even further to basically rule out the following situation, essentially, that if you take any type 2 compactification, if you include any Ramon-Ramon flux, well, there are a few exceptions, but basically any Ramon-Ramon flux, and a fixed, for a fixed Q, any orientifold of that dimension and the d-brane of that dimension. So these are now ingredients that violate the things that we know. For example, neural energy condition could be violated by negative orientifold planes. But still include them with a fixed Q, not more than one. So to fix a Q, you took that, and then, but arbitrary F, with a few exceptions, you can show that grad V is bigger than or equal to CV for some C that you can compute, depending on the case. Okay, again, easy rescaling argument, nothing amazingly difficult to argue. Now, the attempt there in these contexts was not to try to say this is a principle of any kind. It's just they try to use these kind of arguments to say where you should not be looking for the sitter, okay? They say, okay, this you cannot look there, it's not bad, this is bad, this is bad. But luckily, not all of them can be ruled out. So therefore, that was a good sign for having the sitter. You say, okay, good, so we now can narrow our search. That was the main emphasis in these papers, to try to narrow the search for the sitter. Okay. Now, you could also say, look, given that the sitter is hard to get, and given all these no-go theorems, and since there's really no real proof that we have actually constructed the sitter, at least many people believe that's an issue, we might as well contemplate the opposite possibility. What if there's no de Sitter? Suppose de Sitter belongs to the Swampland. What if this is true? Let's just ask the question. Well, I think the fact that we live in de Sitter has been so much ingrained in our thoughts that once you even raise this question, the first reaction is, do you mean string theory is wrong? Right? Because, de Sitter, we live in de Sitter. What do you mean de Sitter belongs to Swampland? It means the whole thing is nonsense. No. So the statement is that the fact that it's ingrained in our head that we live in de Sitter is the thing I want to discuss a little more. How do we know we live in de Sitter? Well, we have measured dark energy. Well, do we know the dark energy is fixed? Well, is it constant in time? Well, there are strong bounds. For example, and I will try to mention these bounds. If you say, well, we are not, the dark energy is some wave of some field and it's not fixed, it would roll. And in fact, you can bound the potential, the slope of that potential based on observation. In the past epoch, you can see how much, whether the dark energy is changing, and put a bound on it, and you find the gradient of the potential in fundamental units is less than 10 to the minus 122 also. In other words, not only V is small, its slope is also small. It sounds like double fine-tuning. Okay? So this was one of the first reasons that people said, look, come on. You have energy, and also things varying so slowly, this sounds bizarre. Double fine-tuning. One fine-tuning is fine, double fine-tuning is not fine. Now,
but what is the gradient of the ratio to V itself?
I will come to that. I will come to that bound. I'm setting it up. I'm setting it up very carefully. I'm setting up for an anticipation exactly of that question, but thanks for asking. We'll come to that. So this is the bound on the slope we have. It should be very small. And, people say, why not? If de Sitter exists, why not? Of course, grad V equal to 0 is also fine-tuned, but you could say, well, being 0 means, you have stabilized the potential, so it's not abnormal to be there. So as long as there's a good reason, there's something which is a boundary of some region, like 0, it's not a problem. Okay, but the bound here, so therefore suggests the de Sitter. That's one reason people like de Sitter. That's this fact. Another reason, if this guy is rolling, this phi is rolling, it will couple to fields and will change things. For example, if it couples to the standard model and so on, you will get variations of delta of alpha, for example, or the masses of the quarks, or this and that. So you would imagine that this would show up as some variation, and there are strong bounds on these variations. In fact, there's one worse thing that could happen. If the slope is so small, this basically looks like a flat thing. It looks like a massless field. Phi looks like a massless field, and then you can have exchange of this massless field between quarks or whatever they couple to, and it gives you a new kind of force, the fifth force, and again there are strong bounds on the fifth force. So what we learn is that if we are in a rolling situation, then that rolling field cannot couple appreciably to our sector, strongly bounded. Doesn't that sound familiar? Sounds like dark matter sector. So we know there is dark matter, which is weakly coupled to our sector at best. So you would naturally say, okay, this could belong to the dark sector. So that's not a good argument. So the argument, the only thing that sounds like there could be an issue is the fact that the slope seems to be, again, double fine-tuning here going on.
Sorry, so you allow it to couple strongly to the dark sector? Or?
It has to, in some sense.
What happens to structure formation in that case?
Well, the question is how people have actually tried to find the issue, the analog of the force expended between dark matter sector based on exchange of phi, and the variation of that, and the equivalence principle and all that. The bounds are very weak, so we don't have much bound on those. Astrophysicists have begun asking those questions. What do we know about the dark sector and these kind of violations, apparent violations of equivalence principle that this would suggest? There are some bounds, but not very strong. Okay. But anyhow, the statement, the first reaction is, come on, how could this not couple to our field? Is refuted by experimental observation that there is dark sector. So the fact that dark sector is experimentally verified, it better be that in string theory we have a setup where we get dark matter weakly coupled to us. Well, then phi could be part of that sector, that's all. In other words, it could be that the dark energy and the dark matter are unified to one sector, that's it. Not that exotic. For example, it could be in that picture I was drawing, it could be that, this is the standard model piece. The dark sector could be, for example, over here somewhere, and that could be expanding, and that could be the field corresponding to expansion. Or maybe the whole volume of the Calabi-Yau, more naturally or something, is that field, and somehow the middle piece here is kind of frozen by whatever flux. The rest of the manifold is kind of growing. The boundaries are moving away, but there's some frozen kind of thing, which is our sector, maybe. Or maybe pieces that could potentially mix with us, and I will discuss that later. But at any rate, it doesn't have to change our sector.
Sorry, I have a dumb question. Can you explain how this modifies the equivalence principle?
Well, you see, you would imagine that if there's forces between them goes like m squared, you would say, oh, well, it doesn't go like m squared anymore. So that means there's another additional force will look like apparent violation of the equivalence principle. Okay, good. So now, the only fine-tuning we haven't addressed is the slope. in this context. If you assume V is small, then why is double grad V small? So let's say we are not worried about solving the cosmological constant problem, but what would give us the grad V being small at the same time? Two problems. Well, if grad V is somehow related to V, then this would not be that exotic. That is, if the boundary, if the smallest you can make the slope is related to V, you cannot make it any bigger, then this could be perfectly fine with observation. So it's not that fine-tuned. So the whole picture this suggests is that the de Sitter space is not the only way we can connect our present universe, our universe to the present situation. We can have a situation, we have a rolling scalar which couples weakly to our sector, for which the slope is related to V. As we have seen in string theory in many examples, this is not only exotic, it's very typical and this limiting case. So therefore, there is no reason, and that's one of the main lessons I want to give in this talk here today. Models where we have a rolling scalar model of dark energy is supernatural in the context of string theory, and we should study them. It has been studied by a few papers, not as many as they should, and I think that's one thing I think we should study more seriously. Studying what is called the quintessence models of dark energy. Quintessence in this context is just the statement that we have a rolling scalar field with the potential rolling. That's a very natural possibility in string theory. De Sitter is, perhaps we can ask whether it exists or not, but regardless, this is certainly much more natural than de Sitter to get. It's much easier to get, and there's no observational bound which violates it directly, so we could study it. So I think that's perhaps my main lesson here, is quintessence has not been studied as much as it should. Yes?
You say it's easy to get, you mean some two-level calculation, like some supergravity. You gave some examples.
You will have a situation where grad V and V are related. For example, that volume depends. If, for example, that field I'm talking about is related to the volume, we will get such effects similar to this.
But loop correction is not spoiled.
Well, we can talk about loop corrections. I'm just saying that for large manifold, it's certainly true. There could be corrections to that statement. That C could change and whatever.
These are both very small, right? So then the corrections.
No, the ratio I'm talking about. The ratio is some number of order 1. That's my main point.
Is the ratio protected against?
It was. I was in those examples I showed to you that for large volume, it is protected. So we derived it using the supergravity. You have to violate. You have to take the effective corrections into account to change it, which means if the effective corrections of order of 1 over m Planck, the ratio of the curvature to the m Planck is small, then you expect the corrections to be small. You wouldn't expect to be infinitely big if that's small. So it's reasonable to say that that's protected.
What are the bounds on operator mixing between the visible sector and dark sector?
Very good question. We don't know. Well, sorry. The visible sector and dark sector, there are bounds. Of course, people have written, but
but because you're going to allow the quintessence field to couple to the dark sector, so now I can run those things on loops.
Well, the question is, yeah, of course. So this would be very interesting because it suggests that dark sector, if it couples to us, then that field will also couple to us. Yeah. And I will talk about some potential aspects of that, in fact, later. So there's potentially interesting mixing with our sector. There could be. So I'm not saying it's zero interaction. So yeah, there could be. We'll talk about that perhaps. Okay. Good. So let me just then say, if this is the case, it's natural to say, well, maybe this is a criteria for a Swampland condition that the gradient of V is always bigger than or equal to C times V for C positive quantity. So let's contemplate such a possibility, criteria. Could there be such a criteria that grad V is always bigger than V with some proportionality constant C, which may depend on dimension? Well, you might have said, well, we are going too fast here. Why didn't we just say grad V is bigger than some constant? Let's just start with bigger than a constant, universal constant like this. Could that have been the case? No, this cannot be the case. Why not? We have counterexamples in string theory. That's now just like kind of games we play in Swampland kind of thing. You take a possible Swampland criteria, you check it against string construction and see if you have a counterexample which is reliable, which you know you have constructed. Well, what is the counterexample I have in mind? Take Calabi-Yau threefolds. Supersymmetric, we know everything about it. Well, we know many things about it. And there are massive fields, we know for like BPS states in that theory. So there will be a potential of the form 1/2 m squared phi squared, like thing. And if you take grad V, the grad V will go like phi in this case. And you can make arbitrarily small as you approach 0. So there's no such thing. This cannot be possibly true. So this cannot be true. So if you replace this by some function of fields, then most natural simple thing would be something like this. Now, and we have seen examples, no-go theorems and string theory, which fit exactly this pattern. So why not? Let's try to ask that question. Could there be such bounds? And indeed, you could exactly look at this example again. V is 1/2 m phi squared. And if you compute grad V over V for this case, you find this goes like 1/phi. So as phi goes to 0, this becomes very big. So therefore, there's no problem with this bound being bigger. So it's satisfied with the inequality. Now you say, aha, what if we take phi bigger and bigger? Well, we don't trust this description of the potential at any rate for phi big. We know that in particular, phi, a range of field phi bigger than 1, you get all these exotic states and interactions and so on. So this is only near phi equal to 0 at best. So near phi equal to 0, this does not give us a counterexample. So at least there's no counterexample. How about non-supersymmetric bonds? Well, supersymmetric bonds. Supersymmetric bonds, you can have grad V equals 0, like ADS situation, but then V is negative, and this is trivially satisfied. So, and how about supersymmetric bonds with 0 cosmological constant? Again, V equals 0, and that's why equality sign is needed here. So grad V can be 0 when you have V equals 0. So like Calabi-Yau, you can have grad V equal to exactly 0. There's moduli. In some sense, this case is a deformation of the supersymmetric case. If you take any supersymmetric compactification to Minkowski space, you try to deform it to break supersymmetry. What do? You give Vev to fields. But any field Vev will look like this kind of near phi equal to 0 will look like a mass. And therefore, you can see that any supersymmetric theory, slight deformations of it, will not violate this bound either. So therefore, at least this passes the first few checks. And so we could then contemplate the possibility for such a conjecture that grad V could be bigger than or equal to some constant times V for some positive quantity C. I think that's, before I finish, so before I take a break, I want to point one thing out here. Here, we got grad V over V as order 1/phi, and we know that the range of phi could be as large as we want. So in the context of, for example, these distance conjectures for the Swampland, we know that if you go farther and farther, it's not that you stop the distance, it's that you get lighter and lighter modes. So your effective field theory, which ignored those modes, breaks down, but not that it's a problem. So it's a problem if you claim that you don't want any light fields, any additional light fields, or if you trusted your effective field theory description. So one possible version of this conjecture will be to try to say it that way. That is, you get light states. So this is the tower, if you wish, the tower version of this conjecture. Instead of this, you could have said, no, there's no sharp bound like the one I'm saying, but rather you get a tower of light states of the form e to the minus v over v prime with some constant. So this is exactly modeled after this. If you take v over v grad v, this would exactly model after e to the minus the distance. So as you can see, phi is v over grad phi. So you could kind of say you get the tower of light states if you try to go towards de Sitter. Not that de Sitter is impossible. You will get lighter and lighter states in the game. And there is something to say about this conjecture, because you could say Vasiliev theory, for which de Sitter can be done in principle, would be of this type. That is, that in that context, grad v is 0, and you get infinitely many masses higher spin states. So it's possible that if you try to enlarge the story, you might have a situation like this. But let me, for the purposes of today's talk, I will stick with this version, which means that even if this is the true statement, that means this version means that if you violate this, your effective field theory breaks down. So one way or the other, you would translate the question into something like this. Okay, so I think we'll take a break till 11:30, and then I will talk about what implications these will have. So the second part, I want to review the consequences of this constraint, or this potential constraint for Swampland on cosmology. In fact, I want to talk about two possible ones. One is assuming there's a constraint like this, and then also taking into account that the field range is bounded. Now, again, as I said, what this statement means is that your effective field theory breaks down, not that the field distance is bounded. So for a given cosmology, if you want to limit your light states, the tower of light states that you get, there's an effective length scale in field space, which I call delta. Again, I'm dealing with Planck units, so this delta would be order 1 in some sense. We don't know exactly what it is. Some people say it could be like 5 or 10. depending on what model you deal with. Okay, I don't know what's the reasonable delta, but there is more or less some delta. This one, I just want to take one fact here is that both these constraints disappear when you take M Planck to infinity. Namely, if you restore the M Planck into discussion, this will look like this. And if you introduce M Planck here, this looks like this in 4D. I'm dealing with 4D. So as M Planck goes to infinity, there is no restriction on delta phi, and there is no restriction on grad phi, which as it should be. There's no restriction in field theory for sure. So this at best is a gravitational kind of situation. So it's always nice to check that issues that we think are Swampland kind of conditions disappear when you take M Planck to infinity, because we know that you shouldn't get any more condition than the usual effective field theory consistency conditions. Okay, so these are the two things I want to talk about. So let's again divide our discussion to 3 parts. This is I start with the past. So past, again, the paradigm for current description of the early universe is inflation, and I have already talked about this aspect, that delta phi is less than delta. There's already some tension because you find that delta has to be basically in these plateau models bigger than 5. And this is, again, people claim that there may be some models like this, but again, it's borderline at best. So at least there's some tension there, if not ruled out. Yes?
Of course, you get everything fine when you go with Planck to infinity, you get no restrictions, but it still doesn't tell you that you are not going to get any theory. There is a restriction on the theory you will get without gravity, right? And the goal is to find out what are restrictions on a theory without gravity.
Well, that's not, without gravity there's no restriction, other than effective field theory consistency.
So you can have any theory coupled to gravity.
No. Without gravity, I'm saying. With gravity, there are restrictions, and we don't know what the restrictions exactly are.
So it doesn't tell us what they do.
No, I'm saying this is a constraint. Yeah. It's not the only constraint. We just have one of them is presumably this. Now, the inflation models, again, in the context of plateau models, you can ask whether there's any bound on this. You see, I mentioned to you that the natural scenario was kind of a semi-flat kind of a situation like this, and this runs kind of a tension with this situation, where grad V wants to be not small. So the big V is, you would give big grad V. So there would be some tension. And if you look at these plateau models, which are the most favored one, like phi squared and chaotic inflation, all that kind of thing are already ruled out based on some observations of the B mode and the spectral tilt. But the plateau models, like Stravinsky model and so on, are not. And those are the most favored one. If you, in that context, you study it, you find that the value of C has to be less than 0.02 for it to work. So this is means that you have to have relatively flat and long. So there are two issues that you could say, well, you have to solve both, long and relatively flat. Now, if C is 0.02, you remember the numbers I gave you were like 1 or more than 1 and so on typically. It's not easy to get below 1. But, you know, it could be fine-tuned. I don't know. But so again, one cannot rule this out, of course, because I'm not giving a strict statement what C is. But the smaller the C you make, the more likely it is that you have to deal with lighter and lighter states. And one of the issues is, when you talk about inflation, you don't want to get light states, because the energy of the inflaton field will be dissipating to the light modes if you get them. So traversing too long with getting light fields is a big problem. So you have to kind of control that as well. So anyhow, so these are some of the issues. Now you could ask, okay, if I'm saying inflation is in tension, again I say I'm not saying it's ruled out, but certainly it's in some kind of tension. You could say, what are the other alternatives in the context of string theory? I'll just give you one alternative, but this is of course difficult in the context of string theory because we do not know how the high temperature phase of string theory would exactly look like. But if you look at the standard FRW situation, if you like the radius, like e to the lambda, and if you kind of look at the usual situation, what you have is that if you look at the energy profile in the universe as a function of the radius or lambda, you find in the early universe, which is radiation dominated, basically it goes exponentially down like this. And the equations that give you, so if you have an adiabatic expansion, like the universe is expanding with radiation in equilibrium, and if it's dying away like this, you get basically rolling of a potential like this. So you just get a rolling. So this is the usual FRW, can be reformulated in this way as a rolling guy in a potential given by the energy, where you're assuming the adiabatic kind of expansion. Now, we know that this is a problem, because if you go earlier, they will get expansions of pieces which are not causally connected, but they were not causally connected, so that's a problem. And so this rolling of the speedy rolling is a problem. Now, the idea we had with Brandenberger a while back was that, and this is in the context of string gas cosmology, and now I will say it a little more generally, is that this lambda cannot be like this. Why? Well, because as lambda goes to minus infinity, we know there should be additional light states. It cannot be just this, so you get extra light states. For example, if you had r goes to 1 over r symmetry, like a space in a box, you get r to 1 over r symmetry. So in that context, the potential that you will get will have to be some symmetric potential. In other words, the energy as a function of r go from momentum modes to winding modes in that context. So if you have a total entropy in your system, the evolution will not look like this, will look like some plateau kind of things like this. And we studied these kind of models in the context of string gas cosmology. We found that if you get, in the context of string theory, if you get sufficiently close to Hagedorn temperature, the energy in the universe as a function of the radius will look like such a plateau like this. And it looks very much like the picture people draw for the inflaton potential. But in this case, it's literally the statement that the radius does not affect the energy profile for the Hagedorn phase. And why is that? In the Hagedorn phase, the string entropy gets pumped into the oscillating modes. It does not depend on the radius of the universe. So in other words, the fact that it's almost independent of the radius is simply the statement that the energy gets pumped into these local degrees of oscillating degrees of freedom, which don't probe the geometry of space. So this flatness becomes very automatic in that context. Now, in this context, you would have a situation where this guy gets rolled, and then it goes down to the radiation phase. Now it's much slower, and it has time to equilibrate. So unlike the situation with inflation that you have to inflate and then make them equilibrium, since you are having a long, slow evolution, you already equilibrate in the Hagedorn phase. So that solves that problem. And the fluctuation that in the context of inflation is quantum, in this case gets related to temporal, the temperature fluctuations. And to get the similar features like the red tilt and all that for the power spectrum from thermal fluctuations in this case.
The second picture is potential as a function of lambda?
Yes. Potential meaning in this case you fix the total entropy and look at the energy as a function of lambda. So you're assuming an adiabatic evolution, and as a function of the lambda you find what is the total energy content with a given entropy.
But that assumes canonical kinetic term. So it is written.
This is d lambda squared. That's right. Yeah, that's right. Because the radius, as we know, goes like the dr over r squared.
Lambda squared, but you are saying
no. This is dr. So usual kinetic term would look like dr over r squared. Yeah. Yeah, which is like this. Okay. Good. Now, do I believe the detail of this model? No, I don't. But what part of this I might believe? The part of this that I do believe is that when you go to small lambda, the light string state, one way or the other, going to hit us. So FRW cosmology is a no-go from the get-go in string theory. We know that in early universe, you cannot say, okay, I just have this massless stuff, it doesn't matter. We know there are these extended objects. One of the features, and I mentioned this last week, one of the features of any consistent quantum theory of gravity is extended object. Whether it's string, like in Hagedorn phase, or branes, that is part of string theory. So these light modes have to come into play. Have to come into play when you go to such a small distances. If you imagine your space is, for example, a box of tiny size, they will have to play a role. This has not been studied as much. We studied Hagedorn phase, but admittedly we had very limited tool for that. So we considered basically ignoring all the corrections and so on. We turned off the string coupling and so on. So that's of course not defensible because we didn't have any better to do. But the idea that something could temper this behavior is in some sense forced on us because we get new light states and dual pictures that will emerge. So this could be the potential kind of idea, string gas cosmology or brane gas cosmology or some such idea in string theory could be what would replace inflation. This kind of direction has not been explored enough in the context of string theory. Yes?
I mean, these effects are important only at the string scale, right?
Which effects? What do you mean?
What you're talking about.
So here I'm talking about the G string going to 0 in some sense, because I could not otherwise compute things. In this case, M Planck will be much bigger than M string. And so I'm talking about the string equilibrium of string modes, yes.
So in terms of usual inflation scenario, how early, I mean, does this completely replace it, or is it?
No, completely. No. If this is true, you could get everything you want this way. So in other words, the issue of homogeneity and fluctuation could easily arise in this model, and we discussed it already.
Is that natural in terms of the time scale?
Yes. Well, there's one aspect which is not natural in this case or in that case. The question is, how close are you to the Hagedorn temperature? That's the question of entropy of the universe. Mm-hmm. That the analog of the 60E folding, which is put in by the long plateau in the inflation context, which is how long that is, this plateau gets smaller and smaller the smaller the entropy you put in. So you'd ask, okay, why did I choose the adiabatic diagram in such a way that you're close to this? Well, okay, that I have to put in by hand, yes. So there is some input I'm putting. The input means the entropy of the universe is not small. I didn't put, that's a huge number. That is put in by hand, just like the length of the inflaton potential is put in by hand. But they're both equally fine-tuned in that case. In other words, you cannot say this is bad, but that's okay. Either one, there's some aspect that you're doing that you have to fit in our universe. So, however, this is more related to what we see in string theory. That is, the light mode should be, the winding mode should come into play. It is hard for me to believe that you get the temperatures close to Planck and brain and so on do not play any role. That's completely bizarre. So this aspect, which was ignored at the beginning because the people were not doing string theory, could easily be replaced with inflation and so on. But now we have all these other ingredients. I believe we have not been creative enough as a community to explore these directions. That's what I'm trying to remind.
Lambda goes to 0 means R goes to 1. So you actually should not trust anything except lambda goes to infinity region, right?
No, I'm just thinking about if you take a weak perturbation theory, right. You do trust it. It's just T-duality. R goes to 1 over R. This is all I'm saying. Namely, the momentum modes gets related to winding modes. You trust it. You just go to the dual description.
Now your winding modes
winding modes become like the new gravitons.
Yeah, you cannot talk about this unless you...
You cannot talk about, exactly. You cannot, we do it, that's how we get this. Yeah. So we get the lambda goes to minus lambda symmetry precisely by including the winding modes. That's how we get it. That's crucial. So that's stringy ingredients. So stringy ingredients are crucial here. Now, anyhow, this was, in other words, I don't want to destroy inflation and say, well, okay, there's no alternative. There might be alternative, admittedly not as much studied. So I think it would be very interesting to try to develop these further.
If you're talking about winding modes, you're making some assumption of topology.
So in these models that we studied with Robert and with collaborators, the space was a box, the three-dimensional space, and we're just thinking about the toroidal geometry expanding. So the flatness problem in that case was just given by hand with just the torus. So that was not there, but homogeneity and so on emerged just by slow roll of this field.
So I actually, sorry, I was always confused when I heard the talk by the people in cosmology that they would start talking only after electroweak phase or something like that with matter sensor. What you're saying is complete crap because you have...
I didn't say anything is crap. It's just don't put it into my...
What you're saying is that
you cannot start talking about these things from electroweak phase.
I didn't say that. I'm not criticizing their approach. I'm just saying in this context it's natural to have this.
What I'm saying is that in principle you're advocating that you have to start thinking...
You could think also about things which could make sense in the Planckian regime or near the Planck regime by including stringy ingredients. That's all I'm bringing into the question mark. I haven't trapped anything in some sense, but you could say that R goes to 1 over R symmetry means the potential at this point is 0, critical point. So in some sense, you have to, at one point, lambda goes to minus lambda symmetry, means that at that point you have a flat one in that sense. Yes. Okay, I don't want to spend too much time on this because I have many more things to say. So this is the past, present. So present, as we know, the attempt in string theory has been in terms of dark energy with the de Sitter kind of situation. But if you look at the equation of state for the dark matter, there's this quantity W. So in the cosmological constant setup, W should be minus 1. So, of course, if you have a scalar field, the potential, the W will not be 1, and it will roll, depending on... so you have some potential like this. The ratio of pressure to the density is something like this. And W, if phi dot is 0, would be -1. So it could be -1, but it doesn't have to be. It could be close to -1, depending on what is the kinetic term, how much phi is rolling. So you could ask, what are the bounds for W? So if you look at it, for example, as a function of the redshift z, where z equal to 0 is where we are, and let me go all the way to z is 1. So the observations gives you bound. So the observation is perfectly consistent with W being -1 throughout. Okay, so the W is -1, if I want to call this -1. So W being -1 is consistent with all the observation, but there's a range of possibilities, and in particular, you get some kind of a plateau like this, where this point is something like -0.8 or something like that. So the W bound as a function of z with the supernovae up to 2 sigma looks like such a bound. So which means that assuming that W is always bigger than or equal to -1, you're in this regime. Okay, good. So this does not show. I went to more than 1. The 1 was here. So this does not show that that would have to be -1. There's a room for this, and you can just ask in the context of the potential satisfying this constraint, which one, if any, which value of C, is there any value of C, or what value of C would be consistent with this? Of course, C is 0 would be consistent with this constant, but what is the order of magnitude of C that would be consistent with observation? And you find that if you do different values of C, you get pictures like this. So you have this potential like this, but let me just do different color, I guess, here. So you find that, for example, you get a picture like this for W, for C is of order 0.6. So C is of order 1, namely 0.6, is perfectly consistent up to now with observations. Okay. In fact, based on the observations, and if you assume that kind of relation, potential satisfying that, W plus 1 would be bigger than 0.15 C squared based on observations. So depending on what value you get, W today can deviate from -1 by 0.15 times C squared. So depending on what you think that C over there, what order 1 number you think is reasonable, that would be there. Something like this. So anyhow, so this is the kind of bound you get. Again, it could be, let me just again point out, just to make clear, suppose that conjecture is false. It's possible that's false. We do know that the large variety of string theory constructions are naturally have gravity proportional to V, which means that regardless of whether there's de Sitter or not, this should be a natural thing to study, because we get order 1 type numbers, C's like 0.6, could easily fit the current data. So this idea that the quintessence model could be natural is what I really want to emphasize, regardless of whether we believe the conjecture or not. This certainly should be pursued regardless of anything. In fact, let me say something amusing. Suppose we compute the change of log V. Well, okay. Suppose we have a potential V like this. So if you have a potential, then the fact that 10 to the minus 122 is what the value we have is a different version of the cosmological constant problem. So the cosmological constant is not which vacuum we ended up with, but more precisely, where are we now? Because this will be rolling. And typical potentials satisfying the boundary of this are exponential. So the natural flow, very large exponential growth for the phi. In fact, if you compute d log V from the current universe over the course of it, so from the past, infinitely in the past till now, how does log V change? Well, the log V originally, let's say, is order 1 in the Planck unit, so it's order 1 to begin with, log V is 0. So the change in the log V is change in the 10 to the minus 122. It's basically the log of this guy. So the total integral of this throughout the course of the history as a function of phi, so in other words, if you take d log V d phi as the phi rolls, should be about 280 or so if you take this number. What this means is the following. If you parameterize your potential, so you have e to the minus phi times some constant, but more generally, you can write this in the form like this. This is, with no loss of generality, I can write it like this if V is positive, taking into account that phi has a dimension of mass. So you can always write this in terms of d phi over m, which depends on phi, with some mass scale. So the potential could look like this. And what is d log v? Well, d log v is going to be the integral of d phi. If you take the absolute value, you get the integral of this over m sub phi. This should be of the order of 280 for it to be a natural solution to the hierarchy, to the cosmological constant problem, which means if the average of 1 over m phi, so you can write this is mass scale associated to phi, the average of it times delta phi should be about 280. In other words, more precisely, if I introduce so I can rewrite this in the following way. So you can write this as the expectation that 1 over m phi, the average of m phi, let me just take the ratio of it to m Planck, should be of the order of 280 divided by delta phi times m Planck. So this quantity is roughly bound. This is related to delta that I was talking about. It's bounded. The delta phi is bounded by delta. So this is something less than 1 or order 1 or perhaps less, the delta phi in the denominator. But this gives you that the scale of m phi is something related to m Planck over 280 times something of order 1 roughly, which is delta, which is m, let's see whether I get my units right. M phi is this times delta phi over m Planck. This is the average value of this m phi. In other words, the scale you associate to this field phi is, roughly speaking, 200 or about some factor of hundreds less than m Planck times some number order 1. And this is interesting because this is very close to the gut scale. In other words, if you believe that you have a compactification scale that typically sets the geometry more or less similar sizes, the gut scale is roughly related to the volume of these internal geometries. The scale associated with the phi, if that's almost related to the gut scale, you will get a natural explanation of the cosmological constant problem. In other words, in this language, the current cosmological constant will be related to something like this relation, m phi, but if m phi is basically m gut, you would be basically saying that lambda is the order e to the minus some constant times m Planck over m gut. So the point I'm trying to, this kind of relation is not typically used to describe the hierarchy problem, but if m gut is a factor of 100 or 200, whatever, smaller than m Planck, which is currently the kind of right range, this will give you some natural small scale, not as fine-tuned as people imagine. Okay, of course, I do not know these numbers to tell you, to make a precise prediction for m gut, and I don't know exactly why m gut should be m phi, but gives you an idea that the cosmological constant problem gets a completely different reformulation, and these kind of relations can potentially be related to solving it. Yes?
Yeah. So when I look at this problem, it looks like that when Planck mass goes to infinity, phi is infinitely heavy.
What goes to infinity?
Planck mass.
It doesn't go to infinity.
Well, delta phi over mass, Planck mass is order of 1, you said.
It's less than order 1, yes. Less than 1. We don't know how much phi has moved since the beginning, but it should be less than delta.
This formula we cannot take it.
Not to infinity.
Of course not. I'm talking about cosmology after all.
No, I just want to see if phi has a meaning in the field circle. I understand that. But
Phi has a meaning in the field.
No, in this context, I'm strictly talking about cosmology. So m Planck has a finite value. So how about the future? Well, if you take the potential like this, so we would be rolling down here, and the question is, what's next? Well, you could, in principle, have some go negative or continue this and so on. We don't know, but two things could happen. Either you go negative, in which case you go from an expansion to a crunch, or if you go on for a while, if this range is bigger than delta, we get a tower of light states. So either way, depending on whether it goes this way or that way, you have a finite time before there will be a phase transition in the universe. So you can estimate how long that takes, and you find that the number of E foldings, the number of Hubble times that it takes, is of the order of less than of the order of 2 delta over c. So in the Hubble time scale, 10 billion years time scales, in a time scale roughly of order 2 times delta over c, where delta and c are the parameters that went to the conjectures, you will have to undergo a phase transition. This will make the coincidence problem, at least as far as its relation to dark energy, explainable. That is, we are a typical lifetime, a typical time in that universe, before we go to the new universe with a phase transition of some sort, will be of the order of 10 billion years, up to the factors of delta over c, which are over 1. So this would be a different explanation of the coincidence problem, a solution, potential solution to the coincidence problem. Namely, we are about to undergo a transition in a few. Well, 10 billion years is not. Okay, so it's more scary to be lonely for a long, long time. Maybe the new universes are more interesting. Who knows? So this will be quite exciting. So you see, the main thing I'm trying to say is that simple ideas are actually very predictive potentially for our universe. Now, whether these conjectures are true or not, I don't know. I mean, they are motivated by examples. And in fact, so after we gave these talks and papers came out, there were people pointed out various things to us. So let me tell you. So it's hard to believe this is only 1 month ago. But we have quite a bit of interesting follow-ups from different people. So let me explain what has come up since. So immediately after our paper, there was a group of people, Joseph and company, pointed out to us that there are models, potential models, of the sitter already constructed in a reliable way, not the KKLT ones, but different ones, these flux ones. But the problem with them was that it was like this. So you were at the top of the hill. So now, on the other hand, I guess we will hear from Tim tomorrow, perhaps. Yeah. So whether or not, how reliable this may or may not be. So this is still questionable whether or not this is reliable. If this was the case, if you have reliable examples of de Sitter kind of geometries, even though it's unstable, if you have this, then of course this conjecture will be false because grad V will be 0 here at this point. So that would be a potential problem. Now, how do you solve this problem? You could say, if indeed these are reliable examples, you could say that the constraint I'm talking about only applies to V double prime positive, namely the Hessian should be positive. Namely, we're talking about stabilizing modes as much as possible. That's what our intuition is. Namely, the main intuition for the difficulty of de Sitter is not that you want to get some unstable de Sitter. You're interested in getting something which is stable, and there's always this silly extra mode which is hard to stabilize. So in that context, you say, okay, we are only interested in regions of space which is the Hessian is positive, so we're just hoping for stabilizing modes, and nevertheless we can't do it. So in other words, one could in principle say that this is a prerequisite for this conjecture. So that would be a simplest possibility if this is indeed a solution. That I would say that's the least radical one, I would say. There have been other proposals related to this by people, David Andriot, and also Garg and Krishnan wrote the different kind of pictures motivated by the same question, by this kind of example. So people have considered different kind of versions of this conjecture based on this. Diwali and Gomez had a different version of this conjecture, and in fact, they claimed that Diwali claimed that this is already in some form in their previous papers, where they claimed that the fact that this doesn't arise, where they say that the C that I was in the conjecture I was mentioning was a constant. For them, they say it could go all the way up to V, the value of the potential. So in other words, their bounds would be something like grad V squared is less than grad V is less than V squared instead of be bigger than V squared instead of bigger than a constant times V. Okay, I don't know what to say about that, but anyhow, that's another possibility people have raised. Now, more interestingly, in a paper by Tim and Arthur and Frederick, the following was pointed out. Sorry? Denef. So Arthur and Tim, of course, are going to be in the workshop. Tim is going to talk about some aspects, perhaps, but the issue was the following. So we say that there's the Higgs sector, and there's a dark matter, there's a standard sector, and then there's this phi field. How much do they couple together? Suppose we say there's absolutely no coupling between them. So the most natural potential that you would get would be V of H plus V of phi. So if this field phi does not couple at all to this H, then it turns out that if you look at the Higgs potential, we know that we expect it to look like this, where we are over here in the minimum of the Higgs potential. They find that in an infinitesimal region of the origin, this bound will be violated, grad V over V. So if they don't interact, and if it's like this, then you get a violation of the bound at grad V over V's.
They have to interact because they interact symmetric through gravity.
Well, no. Of course they know about that. So the gravitationally they interact. But the question is that is there any other potential mixing between them? That's
Independent.
yeah. That's independent of gravity. So they say if it's like this, then you run into trouble. And so they point out that if you had potentials instead like this, if you have interaction like this, it won't be a trouble. So in other words, they point out that you have to kind of, if you have a complete separation, you will get into trouble like this, unless you do this kind of interaction between them. Now, there are a few possible ways out. First of all, this could happen. This is very easy to arrange in string theory kind of setup. For example, if you have D9 anti-D9 brane, you have a tachyon and you have a dilaton interacting. So this kind of thing is not that exotic. So you can get this. But they also point out if you have this, then you might imagine that there will be a term like this with interaction of the also for quarks, psi bar psi interactions. So they would say, oh, if you have a term like this, then why not a mass term like this? And then if that's the case, then you get into trouble because the mass of these quarks will be varying over time and there are strong bounds on them.
But the H square also would multiply e to the minus 5.
Anyhow, so by rescaling H and so on, you might have issue or not. So depending on whether or not you allow this or not, you could have a problem or not. So the question would be whether you allow an interaction between the phi and the Higgs sector without having much interaction with the rest of the standard model. This may not be unrelated to the question that Martin was asking. That is, the Higgs sector seems to be possibly violating this asymptotic free situation. So it's kind of mixes in some form, perhaps, with the dark sector. We don't know. In which case, this thing may not be that exotic. On the other hand, it would make a strong prediction of what is the structure of the potential. So that would be the positive side on it. On the other hand, if that modification of the conjecture is true, that you have to be this, then this issue that only arises at the metastable point is just off the table because that's the only point, only region where you get into trouble, and so therefore you just delete that discussion. So the V double prime being negative will not apply to the conjecture, would only apply to the regions near the critical points like positive potential. So that would not have an issue with that either. There could be other potential resolutions. For example, nobody has studied H near 0. People have studied H near V. That's where we are now. We don't know exactly how this potential would look like, and so there could be modification of this story. Maybe the Higgs is composite, maybe this and that. I don't know. So the question is on the table, but what this shows is that this conjecture actually could have interesting phenomenological mixtures with the Higgs sector, which actually makes it even more interesting. So
This other conjecture that where you had about global symmetries kind of does it allow this? Because this one is a gravity theory which has a global symmetry.
where's the global symmetry here? What?
Those two V's don't have to be the same.
These two V's? Oh, this is V prime. Sorry, I didn't.
This Mexican head potential has the global symmetry.
No, this is the Higgs. This is just the usual Higgs potential. This SU2 gauge symmetry will tell you. That's the symmetry, gauge symmetry. Gauge symmetry is always allowed in string theory, and that's the usual story. I think I have run over time, so I think I will stop here. Thank you.
If you start with a split Higgs potential as a Higgs, and what about quantum corrections?
So the usual, so in the string theory D9 brane situation, you get quantum correction of the form of e to the minus 2 phi or whatever number. So this is like 1 over lambda squared effect and so on. So yes, you will get corrections, but
If you start with the one above, just from gravity.
oh, this one,
I mean, to the extent we.
yeah, presumably there will be corrections. I mean, they were just studying the situation of their completely split. So there will be some splitting. The main point they make is that if it is to solve it, you will have, it looks appearing as a fine tuning from the effective field theory viewpoint. But that's the nature of the game with the Swampland. So in fact, the very conjecture grad V is bigger than V sounds like fine tuning. So what appears as an effective field theory fine tuning goes with the territory. So I don't have any answer to that question. It's going to look fine tuned Yes.
So I would say from string theory kind of intuition, that entire Lagrangian will multiply it to -5. Right, if pi is a tachyon or something like that.
It could be. That would be the easiest kind of situation to imagine is like that. That is, whatever it is, it multiplies it. But, I mean, I don't have any no-go theorem that cannot be done otherwise. Yeah.
If it's tachyon, right, then...
For example, no, not everything. I mean, it will multiply the open string sector, for example. The closed string sector will have a different story, and so on. There are different powers. Yeah. So you can have different pieces. So this is one piece, the brain anti-brain part of the system.
Pi equals 0,
Well, phi is the field in this case, in this language. H equals 0, you mean? Yeah. Well, it would be interesting to know if there's any potential. The origin of the Higgs potential seems to be the key here. So that'll be an interesting point from the phenomenological viewpoint as well. So we don't know much about that point, other than the theory says the Mexican hat, so we think we know roughly what it is, but we don't have a deep understanding. Anyhow, any other questions? Okay, thank you.